delivering this webinar to PolyU. I mean, just very briefly, Andrea going through his multiple degrees. Andrea got the Italians, you call it the laurea degree, which is not really a bachelor, it's some sort of master. So he obtained his MSc laurea degree at the University of Rome. And he did a second master degree in the UK, University of Sheffield. He was a PhD student in Andrea in France. He was then a postdoc with Professor François Choumet. And he has been working at the University of Montpellier since 2011. He was associate professor and starting from this year, full professor. So we cannot clap here. It's a webinar, so welcome, Andrea, and please go ahead.
Okay, thanks a lot, David, for this very nice introduction. So I'm very pleased and honored to present today, unfortunately remotely, to Hong Kong Polytechnic University. I am going to present our work on robot perception for interacting with humans and for manipulating soft objects. And as David says, I work at the Université de Montpellier in France, and also in a laboratory called l'IRM. The university in France are often associated to a laboratory. So l'IRM is the Laboratory of Computer Science, Robotics and Microelectronics of Montpellier, and it's financed by Université de Montpellier and by the CNRS, which is the National Center for Scientific Research. So a few words about Montpellier. Montpellier is situated in the heart of Mediterranean Europe, in the southwest of France, in a region called Languedoc-Roussillon, which is the fastest growing population in France. And in fact, Montpellier has about 400,000 inhabitants, including 60,000 students. So it's a very young city. And as I was mentioning before to David, it's very sunny, close to the sea, and it's an area of very good red wine. And more specifically, the university is the oldest operating university in France, and also the oldest medical university in Europe, dating back to 1289. The alumni include Petrarch, which is an Italian poet, Rabelais, the French novelist, author of Gargantua and Pantagruel, and Nostradamus, which is not known for literature or science, but more for his prophecies. Then we also hosted and made study many popes, because at the time the popes were sieging in Avignon, not far from Montpellier. And more recently, we also had Oussama Khatib, which you probably know if you're a roboticist. He's one of the pioneers in robotics. And he did his master's in Montpellier before moving to Toulouse and then to Stanford. So currently, our master is in English. So if you're interested in studying in Montpellier, this is the link, and you can contact me because I'm in charge of this master with Professor Abdelaziz. So it's a full course in English that you can follow. And it's one of the best masters in France. So now I'm going to speak a bit about our research, which was carried out in the context of two European projects. A first one, which was called Versatile, which was formed of 9 partners and coordinated by Tecnalia Foundation in Spain. So the purpose of this project was to address 3 industrial cases, one from the automotive industry from Peugeot Citroën, one from the aerospace industry from Airbus, and a consumer good pilot case from BIC. And the idea was to have a robot which was versatile enough to deal with this diversity of situations. So in this context, we designed this robot, which is called Bazaar, and which has the top-notch sensors and actuators in robotics. Then after that, we had a second European project, which started in 2020, which is called Sophia. And the acronym stands for Socio-Physical Interaction Skills for Cooperative Human-Robot Systems in Agile Production. So this project has 12 partners and is coordinated by the Istituto Italiano di Tecnologia, IIT, in Italy. And this project is more human-centered than versatile. So here the idea is to try to understand when the humans have some issues at work, so some psychophysical problem, and to try to have the robot help the human in an industrial scenario. So the robot become assistants, and specifically we address this with 3 kinds of systems: wearable suits which can detect pain, for example, on the human, wearbots like exoskeletons, and cobots, which is more what we address at Université de Montpellier. So these are collaborative robots meant to work with the human. And it's a bit what I will speak about today. So a quick outline of my talk. Here we have a robot. This is a very old robot from my youth, Short Circuit, from a film in the 80s. And if you want this robot to successfully operate in the real world, we have to let it sense and perceive what's going on. So if we draw inspiration from how us humans do this, we would need some vision, some touch, and more in general, some force. So here the difference between force and touch is that force is at a more macroscopic scale, and it includes also the kinesthetics, so how your proprioception lets you know things about the environment. But luckily, all these sensors exist now in the market. Technology provides us with some artificial devices which reproduce these sensors, like the camera on the left, the BioTAC, this is a fingertip which can perceive touch, and ATI force sensor on the bottom. So in this work, I will present how we use these devices to enable the robot to manipulate objects and interact with humans. So we will show this specifically for each sensor, but we will also show some works where we have used multiple sensors, for example, vision and force together, or force and touch together. So just to introduce a bit the subject, I will do a quick recap on what we call sensor-based feedback control. So I'm not sure if all the audience is formed of roboticians, but in any case, I will quickly summarize a few notions. So in general, what we want to do with a robot is a feedback controller, like the one in this figure, where you have some desired task here, S star, and some current task here, S. Then we will subtract one from the other to obtain a task error, which we send to the controller, and the controller does some operations to compute the commands to send to the robot. And we close this feedback loop using sensor data, so the camera, the force, or the tactile sensing. It turns out that most of these controllers can be designed by the following paradigm. You just need to generate a control input U, which minimizes the L2 norm of the task error. So your controller should be the U, which minimizes E square under some task constraints. So this is a quadratic optimization problem, and it has been recently shown in the robotics community that most problems actually are of this type. For example, if you look at inverse kinematics, which is one of the first academic problems that a scholar in robotics will study, this consists in generating the robot axis velocities, Q dot, to control the tool center point velocity and let it follow V star. So here we would have a V star in the scheme. I hope you see my mouse. Otherwise, let me know. And this is the current velocity coming from the robot. And to address this problem, the best way is to write it as a quadratic optimization, where you would minimize the difference between the desired velocity and the Jacobian times q dot. So the solution, if you don't have constraints, is since this is a linear least squares, the solutions will be the pseudo inverse of the Jacobian times b star. Of course, in general, you have some constraints here, so the problem is a bit more difficult to solve. But here you can see clearly that this problem is a quadratic programming problem, and just as in the blue box. So now let's see what happens if we instantiate the same paradigm for our different sensors, starting from vision. So here the scheme has slightly changed. I want to see this image from the camera which is mounted on the robot, but instead I'm seeing this image. Okay, so there's a offset, there's a difference or an error between the two, and I would like to use this error to drive the controller. So this is what is known as visual servoing, and it can be formalized in the following way. For example, by taking a pixel, this is the simplest feature in an image, and you want to see the pixel instead of as xy, you want to see it at x star, y star, as indicated here. So to do this, I will write the velocity error, and I will try to guarantee an asymptotic convergence of this of the pixel velocity. I mean, sorry, of the pixel error. And to do this, we have a model which is the interaction matrix, which is noted as L on this equation, and which is a matrix which relates the velocity of the robot to the speed of the pixel. And then to solve the problem, I should minimize once again the square norm of E. And it turns out the solution here again is a pseudo inverse of L times the error. Here you can see in this video such a controller behaving with 4 pixels. So the robot is moving its camera to see the 4 pixels in the 4 corners of the image. This is work from the group of François Chaumet, which is a world leader in the field of visual servoing. And it's using the equation in red in the figure. So again, you can see this is a quadratic programming problem, and I repeat this a few times because you will hear me speak about quadratic programming a bit today. Okay, then the second sensor I wanted to speak about was force. So here you have a force controller, which is used to close the feedback loop. So this time the reference is a desired force, and the task measured at each instant is the current force. So to do this, there are various ways of doing it. In Montpellier, we use admittance control. So it's also called indirect force control. And here you can see it in this animation of a mass spring system. So you can put a damper as well, and you can model your robot as a mass spring damper, and this makes it soft somehow. So this is the equation you would use. So you would transform the force error into a position velocity acceleration error. And here you can see what happens if you do this on a robot. The person here is touching the robot and moving it around. And all of a sudden, the robot has become soft and friendly somehow, and it's complying with the direction where the person is pushing it. So it's very useful, of course, if you want these robots to interact with people in a safe manner, as I will say later on. But here again, this can be written as a quadratic programming problem, because you will try to minimize, again, the square norm of this error E, and design the controller accordingly. Okay, finally, let's look at what happens with tactile control. So this time we want to use some touch sensor like the BioTac from SynTouch to close the feedback loop. The issue here is this: these sensors are very recent, and I would say they don't have a big market yet. They're mainly used for research, so also this has a bit slowed down their development. And since signal processing, there are some difficulties. In fact, signal processing with these sensors is very challenging because there is a lot of noise, modeling errors. You need to calibrate these sensors when you buy them. And it's very difficult to obtain some repeatability. There are often hysteresis and other fancy nonlinear behaviors. So nowadays, if you want to use tact for control, you would mainly use it to trigger some decisions. I will show some work on this. And so basically use it as a button for the user. And even for this, you need a coarse calibration, but maybe you can just threshold some signal and say, and in this sense, understand if the person is pushing the button or not. But if you want to actually close the feedback loop with desired pressure, for example, and the current pressure that the finger feels, this is today quite difficult because of the issues I mentioned on signal processing. So I don't think there are many works who do this today. And instead, what is more commonly done with these tactile sensors is object recognition. For example, using machine learning, as I will show later on. This is something we have done in Montpellier as well. Okay, so now let's look a bit. So these were a bit the fundamentals that you will need to understand my talk. Now I will speak a bit about the application field, which, as I said, for both European projects, Versatile and Sophia, was the factory of the future. So the factory of the future, the goal is to input some robots in the factory, in particular to reduce the ergonomic problems, which are, for example, the back pain and other kinds of stress which the human workers feel now. And this is a very relevant problem in the European Union because nowadays the highest cost for the health system in the European Union is from work diseases, of course, including burnouts and so on, but also a very important part of this is musculoskeletal problems due to bad posture in the workplace. So the robot should help the person when the person is going to do some bad movements, but at the same time, it is not possible to replace, and also it is not in the intention of the designer to replace the human, because the human has unique adaptability and precision skills. On the other hand, the robot can bring in some power and speed. So in the factory, we can distinguish between two types of tasks, divisible and interactive tasks. So in this drawing, you see it quite well. On the left, the robot and the human are divided, and on the right, they are interacting. And within this second class, you can also distinguish if there is physical interaction, meaning that there is a desired or undesired contact between the robot and human. Or you can push this a bit forward and talk about physical collaboration whenever there is a desired contact, which is actually made to achieve a common goal. So for example, in the photo here, you see that the person is handing over an object. So this is a form of physical collaboration. So in this framework where we want to design such robots, we have three challenges, which are both scientific and engineering challenges. The first one is that you have to have a safe robot. So this is really the prerequisite of any robot working with humans or in human environments. And for this, we have to follow the standards and design methods which can be accepted by the society. The second aspect, which is very important, is that the robot has to recognize the intention of the human. So understand what the human wants to do. And this is not trivial at all, because humans are unique, and each human has its own way of communicating and of moving and of behaving, and the robot has to have some patterns which are common enough to understand humans, but not too common. And also the sensors have to be adapted, and all this has to be done in real time, which is also very challenging. Fast, at least quick enough for the robot to act according to what the human wants. And finally, the third important challenge is that the robot in the factory of the future will have to manage many different objects and materials. And so this is what I call versatile or flexible manipulation, in the sense that it has to deal with a variety of objects and also of different materials, including soft materials. So I will speak a bit about that research as well. So to summarize, we have three challenges: the safety, the human intention recognition, and advanced manipulation skills. So I will now focus on each one. To start, I will speak about safety. So how we addressed safety in Université de Montpellier. And this is a work which dates back a bit. So I will put the sound for this one. So our goal here was to address a standard which is the ISO 10218, which was a standard setting some upper bounds on velocity, force, and power for robots interacting with people. And to do this, we designed an adaptive admittance controller. So basically, the idea is the same as in my previous slides, where you use a mass, spring, and damper to control the robot. So that's why Benjamin in this video can move the robot, as you saw in the previous video, by pushing it around. But the idea was to have this parameter, scalar parameter alpha, which could change depending if you had to bound the velocity, the force, and the power, because in some cases, either of the three can pass the limits which are fixed by the ISO standard. And finally, as you saw in the video, Benjamin is using the tactile sensing for triggering the different actions. So this is a sort of intuitive interface for the human, because he doesn't have to use a sophisticated program or another machine or another computer, but he just touches the fingers of the robot to tell the robot how to change behavior. So it was a quite simple idea, but then drawing on top of this, we continued this research, and Benjamin designed a software library, which is called OpenFree, standing for Open Physical Human Robot Interaction. And here he extended this idea of the ISO. So the figure on the top right is a representation of the standard, but he also was taking into account the motion of the mobile base. So here you have to decide when and how to move the wheels, because in some cases, maybe you just need to move the arm. In some cases, you just need to move the wheels, like here. And in some cases, you need to move both. So as you see in the bottom right of the video, this was represented in the form of constraints, which you put in your quadratic programming. So again, it's a quadratic optimization, and your constraints which turn on and off depending on the situation, our singularity, manipulability, and etc., etc. So this was a bit the kind of things we looked at for the safety aspects to fulfill the standards in the literature. Then let's move over to the second challenge, which is understanding what the human wants to do. So this is the work of Osama Mazar, who ended his PhD a few years ago. And Osama was trying to control a robot using hand gestures. So here you can see Osama doing some sign in the top left of the video. And the robot can recognize this sign and knows that it corresponds to the handover command. So it will prepare its hand to receive the driller from Osama. And the same sign is another handover. So all the signs that Osama was using were from the American Sign Language. So it is a standard way of sign language. And he was using open pose. So open pose, maybe you're aware of this, is a skeleton detector designed at Carnegie Mellon University, and which is very useful to find the skeleton of a person using only RGB images, color images. So first of all, he detects the skeleton. It's the bottom left video where you can see the blue dots corresponding to his joints. And then he builds a squared region of interest, which is green, to find the hand of the person. And for the hand, he started from a pre-trained convolutional neural network, which is Inception. And then he kept training it in the lab with a data set from the people in the lab on the American Sign Language. Finally, the system was integrated in Open3. So this could enable using it in real time and also with all the rest of the safety criteria used within Open3. So intention can also be found in terms of force, not only with vision. So Sony here, Sony Tarburiyesh, who did his PhD with us and with Technalia, the company, was using force and vision to control this robot, which has 2 arms. So when you do some admittance control, a very important aspect is to understand where the person is applying the force, because you don't have a measure on the table, for instance, in this example, but the measure is only at the end effectors here, where you see my mouse. So there is a lever effect. You don't know where exactly the person is applying the force. And that's why he was using open pose to find the skeleton in the image. So if you don't know the interaction point, it becomes very, very difficult to do this operation. Here you can see users doing it without the robot knowing where they are pushing. So they also have a virtual reality system to drive the task. So the virtual reality is just used to tell the person where it should put the table here. And you can see they're struggling a bit. The novelty also in this system is that the system is with dual arms. So this is going to bring up a bit the follow-up of the presentation today. So instead of just using one arm, Sony designed representation of task for bimanual cooperative operation, which was quite novel, in particular for admittance control. So the 2 arms are controlling admittance, but in a cooperative fashion. I will explain better later. So here you can see when the robot knows where the person is applying the force. So this is thanks to open pose on the top right of the video. Then everything is smoother, and for the users it's much simpler because the robot knows when you want to do a vertical translation or a rotation. It can tell because it knows the application point of the force. So Sony also developed hierarchical quadratic programming system to control both arms and also the wheels. And this is kind of the follow-up of the Open3 library, and it's another library which is the one we are using the most now, and it's called RKCL. And as I mentioned, he also integrated open pose to estimate the contact position of the person in the robot space, the robot workspace. So now we'll move over to the next part, which is versatile and flexible manipulation. So the first work was from Zineb Abderrahman a few years back. She looked at zero-shot haptic recognition. So if you have traditional multi-class classification in machine learning, you show a classifier a few objects like a bottle, an apple, and an orange, and then the day the classifier sees a bottle again, it knows it's a bottle. So this is common in image processing nowadays. But the problem is that in real life you have, or for also in the factory, for example, you have many daily life objects, and you cannot train your classifier on each one of them. Maybe one day you have a new object and your classifier is not ready yet. So the very nice idea in Zineb's thesis was to do some zero-shot learning, which is common in image processing, but not in haptic or tactile systems. So here, the classifier is trained on a bottle, an apple, and an orange, but it can classify a ball. And how this works is that it has the attributes, so some characteristics of bottle, apple, and orange, and it's actually not really learning to classify bottle, apple, and orange, but rather to classify the attributes, to know what is a sphere, what is a plastic, what is metal, and so on. So this is a short video explaining this. She was using the shadow hand, which you see here. So it's this very sophisticated robotic hand with fingertips. And she was using probabilistic Bayesian learning and handing over many objects to the hand. She had a classifier based on the shape of the hand, which was needed to find the shape of the object, and one with the biotac for finding the material, because the biotac can measure the temperature, so you can infer somehow the material. So she trains and learns a lot of characteristics, for example, cylinder or metal or plastic or concave or convex, etc. And then if you give it a new object, which is not a learned object, but it has attributes which have been learned, then it's capable of classifying it. So, for example, this object was not given to the training before, but the attributes are known, and then the algorithm can classify it nevertheless. So afterwards, she integrated vision in this. So she was using also visual data and switched from this Bayesian learning to convolutional neural networks to integrate vision and touch. And of course, the results were even better because she could also see what the robot was touching. Some follow-ups in that work. So then the question we wanted to answer was, what happens if you have a novel object which you have really never seen before? How can you know which object it is? So you have some metric here, which is called a novelty detection, which is a probabilistic function, which tells you, I know this object, so I can use a standard classifier because I've been trained on it, or it's a new object I've never seen before. And this is, of course, a difficult problem because you don't have, you have never trained these fully connected layers. This is a neural network here, which is not trained. So how do you manage when you have this neural network, which is not trained? So Zineb had a very brilliant idea, inspired by what is done again in the image community. So she looked at adversarial training to generate synthetic data. So since there is no data to train this guy, we're gonna generate some synthetic data to train it. And for this, you have architecture in deep learning, which is called the GAN, Generative Adversarial Training, where you have a generator which generates some synthetic data. It's named G here, and the discriminator named D, which has to tell if it's real or synthetic. And you train them alternatively. A bit of, first you train a bit D, then you train a bit G, and back and forth, so that G learns to cheat D, and D learns to guess what G is producing. And once your training is good enough, and particularly the generator is good enough, then you can unplug this part and instead plug your neural network, and the generator will be capable of generating data which is sufficiently realistic to be used to train this novelty classifier. Okay, so this was a bit about how to recognize novel objects in the environment. Now I'm going to continue on more recent things we did on soft objects. So in factories or in the real life in general, you can have many objects which are not rigid. And while roboticists have worked a lot on manipulating rigid objects. Little has been done on soft objects. So one of the pioneers in this is David Navarro, as you may know. And Jiong Zhu, which also was in Poly Hong Kong a few years ago, hosted by David, looked at how to reproduce this kind of task, which is done in the factory. So to place a cable along contacts. And he designed this particular tool for the right hand of Bazaar, which was capable of letting the cable slide or also block it if you push against the table. So here you are letting, you can pull the cable and then sometimes you can fix it. And it's quite ingenious mechanical system. And here you're using eye in hand camera. There's a camera here, you see a real sense, which is mounted on the tool, which lets you see very closely near the cable tip. And just using this image processing system, we can, and also with a particular formalism. So Jiong designed a contact mobility index, which was a metric to tell whether the contact was constraining the cable or not. So depending on this index, the robot would pull the cable or it would turn the cable. So it would alternate between two actions. So this is a very simple planner with vision-based control also integrated within it. So this was followed up by some work with Celia, which is very recent actually. Celia is doing her PhD thesis in the context of Sophia. So she, here you can see, I just put a pause. So this is roughly the paradigm that we were using for dual arm control, which you also saw in the video with the virtual reality. It's a cooperative task representation. This means that rather than controlling the two end effectors separately, we control them together. And for this, we have two tasks. One is the absolute task, so where we want to work, and the other is the relative task, so how we place one arm with regards to the other. Okay, and for some things, you don't really care about the absolute task. For example, if you want to hold an object in the air, what is really important is the relative task because you don't want to drop the object. And so knowing this can release some degrees of freedom. So it's very important for such a redundant robot to have extra degrees of freedom. So this is a bit the framework where we worked, and she integrated also work for Jiong, which Jiong did when he was in Hong Kong. So here she's using a depth image, which is a novelty with regards to what Jiong was doing, to get the contour of this object. And using principal component analysis, she extracts the relevant features of this object and then uses this to control the two arms of the robot. So it's a bit follow-up of things that we had been doing with David Navarro and Jiong Zhu, but extended to this dual arm and also to a three-dimensional object where you also have a point cloud and not just RGB image. So here you can see in blue the current shape of the object, and in red the desired shape of the object. And here she's also doing it with a rigid cardboard. It's also, again, interesting to understand that you don't necessarily need the absolute task for such problems. Sometimes you just want to deform the object, but you don't care about its position in space. And that's where we think that this kinematic representation is better than a traditional one, where you would control everything. And these are other experiments she did. This is another work also on soft materials. It's work I did while I was on sabbatical at QUT in Brisbane, Australia, working with Peter Cork and colleagues. And this is, this time I was looking at plastic materials, so molding, for example, flour or sand like this. So first of all, we wanted to understand how humans do this. So we built a data set where people were shaping the sand, and we filmed this behavior. So then the purpose was to use this data set and to control a robot, and also compare 3 alternative control strategies for the robot to do this itself. And we showed that it converged to a desired error in all cases. So the proposed method is to use such fancy tool to deform the sand. And the goal is to obtain a desired image. So again, it's a quadratic programming problem where the robot should apply some actions. And we had some hypotheses about a feasible shape. And also we were looking at just 2 actions, a pushing and a tapping action. So the pushing action, which is actually the most interesting one here, consists in deforming the contour as in red. So the corresponding feature is the series of pixels which compose the contour. Whereas the tapping action, the tapping feature is the texture of the image. So the control strategy, ideally we have a feature, we have a state vector, and we could use the image-based visual surveying, the one I showed you in one of the first slides. But to do this, we should know this matrix L, which maybe you remember from my first slides, yet this is not available. So instead, we have to find an alternative. So we explored 3 possibilities, taking the average, the maximum, or a neural network to understand how to move the robot, looking at the current and desired contour. So we designed this neural network first. I will probably go a bit fast on this. So basically, we took all the images in the data set. We segmented them to extract primitive motion. So this is the motion a person does while it is pushing the sand. Then we take pairs of these contours. So these will be input to our neural network. I want to go from this contour to this contour. Which action do I need? And of course, I have the labels because this is the ground truth. This is the beginning of the action and the end of an action. And then I can train this neural network to predict which action is necessary to go from this contour to this contour. So from the blue here to the blue here, how do I have to move my robot? And the results are shown in this video. So here, the robot has to obtain this shape. So it's moving the tool around to obtain it. And it has different options with the 3 techniques I mentioned. It can take the average of the 2 contours, the maximum of the 2 contours, or the neural network, which was trained with human data. So these are the arrows that you see, the green and the cyan arrow. And as you can see, it eventually converges to the shape somehow which is desired. So we did benchmark this with the 3 shapes like this, and we obtained such results, which were not too bad, considering that the robot does not have a point, a tool point, but it has a square tool. And to check the validity, we looked at the mutual information, and we can see that it converges in all 3 experiments and with all 3 methods, yet the average is not very good. It's the red curve. On the other hand, the neural network is fast at the beginning, but it's not very efficient when the errors are small. And for the maximum, it's the opposite. It will converge slowly, but then efficiently for small errors. I will skip this because this maybe I can just show it quickly. This is the follow-up of that work. So we looked at how to do this with a hand, and this is a work in progress a bit. We haven't submitted it yet. So basically, we are doing the similar thing with the hand. So we try to predict what happens when we do an action with the hand on this sand. Then we have a planner which plans how to go from the initial shape to the final shape. So which actions it should take. And for this, it's convolutional autoencoders that we use to train the system to predict the final shape. And the results are shown, well, I'm going a bit fast. So here the robot is applying various actions to obtain a desired image, as you can see here. So I will just conclude now because it's time. So I showed you a bit of these three problems. My conclusions will be more oral and maybe in the question time, but roughly I would say that safety, we're not at all far from reaching it. I think you already can see robots in the factories, or because most things have been dealt with also using admittance control, or even better torque controlled robots like the Franca Panda. Human intention recognition is really an active field right now. So I think there's work to do, but OpenPose, the system I showed you for recognizing the skeletons, is very useful. But before we can actually use this in a real environment, there's a bit of work to be done, in particular to deal with noisy and unreliable sensors and managing this in real time. And finally, what I showed to you about manipulating soft objects or recognizing objects never seen before, I think is more fundamental research for now. So I would say this is more something which will maybe or maybe not work in 10 years or so. These are people who have contributed to all this work. And finally, this is a list of the publications which I cited today. So that's all for me. Thank you very much for your patience and for listening. I hope you enjoyed it.
Okay, thank you. Thanks so much, Andrea. Very interesting work. I never seen a presentation of yours, to be honest. I mean, like this. I've seen your papers and follow you for many years, but never a talk. All right, so we have time for some questions. We have 89 people today. This is a record, I must say. Yeah, we never get so many people to a seminar, so you really brought a lot of guests today. So anyone wants to ask a question, you're welcome to unmute yourself and even your camera if possible. And anyone attending the webinar would like to ask something. If nobody asks something, I will go with my students and force them to ask something. So go ahead.
Oh, please don't do that.
They know already that they have to ask. So
any?
All right, there's a question from Luo Heng. He says, as neural networks are hard to interpret and will cause some undesired outcome, will neural networks cause some safety problems? Well, you can read it actually.
Yeah, I can read it. Yeah, it's very relevant questions. I really like discussing about this deep learning because it's very actual now. Sorry, I'm not sure you see me. So yes, I agree with you. So in fact, the things we tried with the neural networks did not always convince me, and I think that it's definitely, I mean, in my viewpoint, I think that machine learning is very useful in all problems where there's no safety concerns. A very popular example is completing your SMS messages on your phone, you know, when you predict what I'm going to write in an SMS. Well, of course, I can have some problems with my wife if I write the wrong SMS, but my life should not be endangered because, as you say, the output is unpredictable, but if it's something which is not going to put me in danger, it's different. If you look at autonomous vehicles and robots, then I'm a bit more reluctant. So I still think the neural networks are very important for perception problems. Again, as long as there is a safety layer underneath, which checks that nothing dangerous is going to happen. But clearly they worked very well in perception. And the reason is that we had all this data in perception. But for control, I'm not very fond of machine learning because we need also data, and to build the data, we need to make the robots move a lot. And as you emphasize in your question, it can be dangerous to use these black boxes to control a dangerous mechanical system. So yeah, I think I'm not sure it's a good idea. Thanks for the question.
All right, thanks. Do we have any other question? We do. Thanks very much, he says. There's another. Okay. I will read it in case somebody is not reading. So he says, thank you for your talk. If I use admittance control and compliant control interchangeably, do I make a mistake?
Right. Wow. Okay, thanks. Yeah, so I never did it actually, because we always used admittance control. It was the shortcut because we did not have a reliable dynamic model of our robots. So it's a bit of a hack, but it works very well. It's true that nowadays it would be wiser to go towards compliant control, especially if we have platforms like Panda, Franca Panda, or other platforms where you can do the torque control. But I think you can do them interchangeably. I have seen, I remember a old paper, but very famous, by Christian Ott, where they do this. Christian Ott from DLR in Munich, and they actually put an admittance loop outside an impedance loop. So I think it's a good idea to do it. I would say the compliance control is really the lower level safety. So it's good if you have it all the time running, if you have the dynamic model. And the admittance controller is more related to the task. So this depends on what you want to do. So you should always have the compliance control, for example, even for a robot that's doing some stupid pick and place, because if a person touches it, it will adapt. But admittance control is more for the tasks. So for example, the tasks you saw where we want to move the driller, there you need the admittance control on top. So I would say that's task specific, but if you have a compliant control, that's more important. You should have it all the time. But I reckon it's more difficult to design because you need a dynamic model and torque, and you need to control the torque of your robot. So thanks for this question. I'm impressed by the questions. High quality.
High quality. They've been rehearsed beforehand. Don't worry, Andrea. We're prepared for this.
I don't believe you.
All right, there's another one. When grabbing brittle matters or objects like an egg, for example, how does the mechanical arm control the force required such that it will not break it, the egg, if the force sensor only depends on the restoring force? Oh yeah. So by measuring, with the at the tip, or maybe just by using force or tactile sensors, how would you ensure that you will not break a brittle object like an egg or a crystal? I may extend here.
I'm not sure. Well, I'm not sure I'm gonna answer because maybe I did not fully understand, but I think so currently I don't think well, I think for this problem, first of all, you need touch, and as I mentioned, I'm not sure today we have good enough touch sensors, but I'm optimistic that we will have them sooner or later. And then if you have a good touch sensor, so if you can measure a force on the fingertips, I would stick to this admittance control framework. So I would transform this force task, which is do not apply too much force, into a position task, which is if the force is too high, open a bit. So normally the admittance controller could take care of grasping an egg, but the prerequisite, which nowadays is not true, is that you need a good, very good touch sensing, calibrated touch sensing, which we don't have. But if you can measure the forces, I would just make a mass spring damper on each fingertip, which controls a desired force. Then another story is how do you define the force which you need to hold an egg without breaking it? But that's more an engineering problem. I don't know if I replied. Maybe you can write in the chat.
Should be fine.
Jeffrey, if you're happy.
Any other questions from the many topics presented today? Wow, 2 questions.
Jeff, oh my gosh. Okay, so this, I think
these are groupies. So it says, hello, Professor Andrea. Thanks for this great talk. Question number 1.
Sorry, yeah.
He has 2, all right. Since we see many works on either control-based or learning-based methods, can you share some points about combining control and learning-based techniques? 2 different worlds. I will go into different, it's not a dichotomy. There's a lot of overlap. And how can they be combined? Is it promising?
Yeah, so thanks a lot. Yeah, I would more speak about data-based and model-based, maybe, because yeah, if you have a model, for sure, if your model is reliable, then you can use this more classic control, and it should work. You don't have to. So there's a lot of course, attraction for the deep learning. I think it's because it works well and it's because it's easy to use. So also for students, it's very attractive. And we, the old guys, I'm older than David, but I think he's getting old too, maybe for this, are not too fond of this approach, because I think, yeah, learning is nice and cool, and it's very attractive, but it stays a black box. So if you can get a model, it's better. On the other hand, I'm really thinking more and more that it's becoming fundamental for so many problems when you go in the real life, because so many things cannot be modeled. So for me, the future is really to combine them. And that's what we try to do more and more. I think you've seen a bit of it in this video where we, for example, in the hand gesture, we were doing the machine learning to see the hand, but then we still control the robot with classic methods. And I don't believe in this end-to-end deep learning, which it's a bit the question I answered before about controlling with learning. You can do it if you have a Google farm where you have 100 robots doing a task, but it's not really sustainable economically. So in practice, you cannot train a robot for control. So yeah, I think you need a bit of both. And even OpenPose, when you look, it needs, now we're trying to do some filtering on the OpenPose data, and we use the Kalman filter and quadratic programming to correct the output of the skeleton, because sometimes OpenPose gives you horrible skeletons of the person, and you need some model behind it. So I'm very excited about this. I really think that is going to improve it. But the problem is that it's 2 communities which tend to be a bit elitist. So now they're starting to talk to each other. So hopefully it will evolve. And the question 2, the future of deformable object manipulation. So I think David also knows. And we have.
How many years can we milk this problem, Andrea?
Say that again?
For how many years do you think we can still milk the problem?
Yeah, I think so. I mean, it's very hard to tell, because it's true that the problem is very popular nowadays. but it also sometimes looks like maybe it's because researchers create their own problems sometimes just to pay their salaries or keep themselves busy. On the other hand, so I think some things can be done very simply in deformable object manipulation. But actually, as I started doing it, I realized how much industrials were interested. So probably it's not just milking, because it turns out that, for example, for the cable, the things we did with the cable, there was so much interest from car companies and from Airbus. And I think there is a lot of interest. But of course, and that's typically a field where I really believe the question one is the answer. So you have to use data-based and model-based. It's a bit what we are doing with Celia's PhD. And then it's always the same. For me, we need an application. So robotics progresses if it's useful for society. So I think there are applications of deformable object manipulation, but only time will tell, I would say. So if there is industry interested, and then everything goes faster. It's like autonomous guidance, or the what's it called? The Hoover, the Roomba. This was an application and people designed the Roomba. But when you look at humanoid robots, we've been speaking about humanoid robots for 20 years. The Asimo was working 20 years ago, and we still don't see any humanoids in town. So,
yeah. All right, Madame Cho, how are we doing with time?
Yes, it's
we good?
Already overtime.
Sorry, one more thing. Andrea, any information you might want to share regarding entry to your master program or open PhD positions? You know, you have a big audience here. Do you have any openings?
Yes, for sure. Yes. So the masters, there is this link on the slide. So master is in English. It's 1 year, and it's starts in September until September, and there is an application to do. And the interesting thing is that in France, as you may know, education is very cheap as compared to Anglo-Saxon places. So you will get English taught master, but the entry fee is not expensive as in the UK or in the US, very far from that. So please contact me if you're interested in applying. For a PhD, we will have openings probably with the SOFIA project in the field of, so it's the human intention recognition. So using the pose of the person and a bit the question Jeffrey asked. So fitting some data and the model to improve the skeleton. So we want to really have a good skeleton recognition, and then also activity recognition with machine learning, because we think it's really important for the robot to see a person and see what it's doing, and now it's not working so well. So I think it's a very nice PhD in a European project merging model-based and data-based approaches. And also contact me. I should start well. If we have good candidates, we can start before the summer, or otherwise more likely in September.
Right, thank you so much, Andrea. Thanks a lot. We really enjoy it. Madame Cho.
So this is the end. This is the end of the webinar. So many thanks again for Professor Cherubini. And thank you all for joining us today. This is the end of the webinar, and we will have another webinar in the coming month. You are also welcome to join us again. So that's all today. Thank you again. Big thanks to Professor Cherubini. Hope we can see you, meet you soon.
Thank you.
Okay, that's all. Bye-bye. Thank you.
Bye-bye. Thank you.
All right. Wow. So many people attending today, Andrew. Actually, Karen, am I wrong? This is the one who has attracted the most people so far, right? There you go. Very good. Very good. Do you know why? Do you know why, Karen?
Because of our guest speakers.
Because of the speaker?
Of course.
Of course. So,
definitely.
And who invited the speaker, may I ask? the department should ask me to bring, more top speakers like this. Thanks so much, Andrea.
Our Dr.
Yeah,
David.
you're welcome.
Alago. Thank you so much. Thank you so much. Our
you,
Dr.
Karen.
Navarro
Thank you.
Alago. So very successful webinar ever today.
Karen was practicing the pronunciation of Cherubini for maybe 2 months.
Cherubini.
Cherubini. She was constantly saying Cherubini, Cherubini.
Cherubini.
I don't worry. Most French people here, they still don't know. So
It's a Cherubini. All right.
So yeah, I think there are still participants, but anyway. But yeah, I hope I can come visit you in Hong Kong.
Sure.
Because we still have a project with David, and then we can meet also Karen in person.